Welcome, wonderful people. This is Mr. Ndabezita, and we are looking at physics, grade 12. We will be looking at an inclined plane. So, let me just draw for you what is provided to us. We have this, and something like this. This is what we have. The angle here it's 50 and the angle there it's 30, and there's an object of mass 70 kilogram. There's an object of mass 50 kilogram. This is M1 and this is M2, and both of these are being pulled by a string in this way. So there's a pulley, forgive me for the drawing, but this is what the pulley is. So the objects are being pulled. This is A, this is B, and this is C, and we are told from A to B this is a smooth. So from A to B this is a smooth surface, and from B to C this is a rough surface. Okay, so they say two blocks are attached to each other by a light inextensible string moving over a frictionless pulley as shown in the diagram. The slope AB has a rough surface. AB has a rough the slope AB has a smooth surface and makes an angle of 50 with the horizontal, and the slope BC has a rough surface and makes an angle of 30 with the horizontal. And in 2.1 they say that we should state Newton's second law in words. You will state this based on the prescribed manual that you have of physics, but Newton's second law just simply means that the net resultant force acting on an object will be equal to the product of the mass and acceleration. That's exactly what it means. And then you will state that I will not state Newton's second law. And then in 2.2 they say the coefficient of kinetic friction between slope BC and the block M2 is 0.2. So Fk between BC, the coefficient of kinetic friction, mu k between B and C is 0.2. The coefficient of kinetic friction between slope BC and the block M2 is 0.2. So moving from B to C, there's a friction that is acting, and the mu k, the coefficient of kinetic friction, is 0.2. Okay, that's fine. And then in 2.2.1 they say that we should draw a labeled free body diagram for block M2, and 4 mark is provided for this. I know that a free body diagram is represented with a dot. That will represent an object of mass 70 kilogram. Now, because the object is resting on an incline, it is at an angle, I know that I will have the normal force. So the normal force cannot be like this. This has to be the normal force because it acts from an object. Okay, so I will have my normal force. So I will say F normal. You can write it like this, Fn, or you can just say capital N. That will denote the normal force. And then once we have this normal force, we know that the normal force is always counterbalanced by the gravitational force, so which is the weight, the component of the weight, because I know that weight will always be directed downwards. and I know sum of the normal force and the weight must be equals to 0, since the object is not going upwards or downwards. So we are in essence saying the magnitude of the normal force, in other words, has to be equals to the weight. So this equals this, and this you can say this is just weight, or you can say this is mass multiplied by gravity, or you can say this is Fg, capital F with a small letter g. That will denote the weight, and it is always directed downwards, something worthy of noting. And then one thing that I should be aware and careful of is, if this is M1 50, oh, is this 50? Let me check so that I don't make a mistake. Sorry, this is 12. Forgive me. This is 12 kilogram. This is 12. So if this is 12 at an angle of 50 and this is 70 at an angle of 30, I don't know whether the system is going up, or the system is going down, or the system is going to the left, or the system is going to the right. So I will have to draw two free body diagrams here, assuming the first one that the motion goes to the left, and another free body diagram assuming that the motion is going to the right. I hope this makes sense, because I was never told that the system accelerates to the right or accelerates to the left. I was just told that this is M1, M2 with this mass, this one at this angle, this is smooth and this is rough, and that's all what was said. Now, in this free body diagram, I'm going to assume that the motion is going to the left in this one. So if the motion is going to the left, that means the tension is going in that direction. The tension will be the pulling force. So it is pulling the 70 kilogram block to that side. So because it is tension that is doing work, positive work, moving this upwards, the length has to be longer. And what is this? I'm going to say this is my force of tension. This is my force of tension. You can write it in this way, or you can just use capital T. That will denote the tension. Okay, and the length of the arrow is the size, the magnitude, and the arrowhead point in the direction of motion. This is me assuming that the motion is to the left. So tension does positive work as we go to the left. I know that you understand this, okay? And if you do, which I know you do, I know that as the object is going up, there's a friction between from B to C, so there is a force that is opposing the movement of this object. And which force is that? That is the tension force. So that is the frictional force, and friction has to be smaller than tension, since tension is the one doing work. So I'm going to have my force of friction like this, or you can just have small letter F. You can say capital F with a small f, that is the force of friction, or you can just write F, small letter f, to denote friction. And I know that friction will always oppose the movement of an object. If an object is going up, friction will always go in the opposite direction. Okay, but I know that this object, because it is resting on an incline, as this object is going up, there is a component of weight that is trying to pull this object down, which we will call mg parallel, if you still remember this. So and it is a very, very small value. That value is even smaller than the frictional force. So I know that my drawing it's not very good, but allow me to just try to just bring them closer like this, and I'm going to say this one is mg parallel. You can write it like this as mg parallel, or you can write it as weight parallel, or you can write it as fg parallel. I'm very, very sorry guys for bringing them this in this way. I'm very sorry for that, but this is exactly what is happening. You must always know that the magnitude of mg parallel will be, in this case, smaller than the magnitude of the frictional force. Something that is worthy of noting. I'm not saying it will always be like this for every situation, but for this one, I surely believe that it has to be in this way. And the calculations will prove whether what we are saying is true or not. After we have done some calculations, we will go back to this, and you will see that we were indeed correct when we said that the magnitude of the force of friction will be smaller than mg parallel. You will see that, don't worry. And then once I have this, I can go back and say, okay, I know that the normal force has to be counterbalanced by what? By Fg perpendicular. And this Fg perpendicular has to be equal to the normal force, since they are equal but opposite in direction. They are equal but opposite in direction. So this is something that we have to know. So the normal force is equals to the component of the weight, which is Fg parallel, Fg perpendicular, because Fg perpendicular and the normal force are not doing work as this object is moving up or down. So I will draw my Fg perpendicular. You can say Fg perpendicular like this, or you can say weight perpendicular in this way, or you can say mg perpendicular. So there are different ways in which we can write that. And then when all is said and done, this is us assuming that the motion is to the left. So if the motion is to the left, there are two forces that are opposing the tension force, which is friction and weight parallel. Something that is worthy of noting. Now, in the second diagram, that is me assuming that the motion is to the right, then I can do the following. I can say, okay, if the motion is to the right, so that means the component of the weight is the one pulling the object downwards. And if it is pulling the object downwards, I know, in other words, that tension and friction will be in the same direction. Something that is worthy of noting. So I will say, okay, if that is true, that the component of the weight is the one pulling the object down, so how am I going to show this? So I'm going to say, okay, this is fine. So if the motion is to the right, that is to say, this object is going down. So what is pulling the object down? It is weight parallel, and meaning tension is going up together with friction, because as the object is going down, friction is opposing the movement of this object, therefore friction is going up. In that sense, friction and tension are in the same direction. Okay, that's fine. So how am I going to represent this? That is another question. Now I can always have, as this object is going down, I will still have my normal force, and I know I can just say F normal, or you can say N, and I know that this normal force will be counterbalanced by the weight component, which I will call Fg perpendicular. Okay, and then I know that as this object is going down, tension is going up, and it is in the same direction with the friction. So I can say, okay, let me have my force of tension, which is in the same direction as my force of friction. Okay, and let me have my component of the weight, which I can write as Fg parallel. And this is what I have. This is exactly what I have. So this is assuming that the object is to the left. This is assuming that the object is to the right. I hope that we are fine, wonderful people. I hope that we are fine. Right, being that as it may, I think we have answered 2.2.1. And we can try to go to 2.2.2. And in 2.2.2, they say calculate the magnitude of the acceleration of the system. Show all the steps in your calculations. The magnitude of the acceleration of the system. Now, whether you go for this free body diagram, whether you go for that free body diagram, the answer will be the same. But we will do for both so that you see exactly what I mean. So we will start with this one. We will apply Newton's second law, that the net resultant force, which is sum of all the forces that are doing work, is equals to the product of the mass and the acceleration. So with this one, I am going to allow this to be positive, so these ones are going to be negative. So I'm going to say force of tension minus, because they are acting in opposite directions, as you can see. So I'm going to minus force of friction, and I'm also going to minus Fg parallel, and I'm going to say this is equals to the mass 70 kilogram times A. Do I have the force of tension? No. Do I have the force of friction? No. But I know that with the mu k, I can find the force of friction, because I know that force of friction equals mu k times the normal force. And I know that the normal force is equals to weight perpendicular. So this is mu k mg, and this what is this? This Fg perpendicular, we should always know and understand that the mg perpendicular, Fg perpendicular, will always and always be equals to the cosine of the angle. So you take your UK, I know that normal force will be equals to the weight multiplied by the cosine of the angle that it makes. Something that is worthy of note. Alright, so I can just come here and say force of tension minus UK mg, the cosine of theta, minus, I know that FG parallel is mg, the sine of theta, this one, and this is 70A. Okay, so force of tension minus mu k was given as 0.2. We are talking of an object of mass 70. The gravitational acceleration pulls everything with an acceleration of 9.8 meters per second squared. The cosine, what is the angle that it makes? The angle is 30. The angle is 30. Okay, because we are speaking of M2. We are speaking of M2, angle 30. Remember, this free body diagram is for M2. So mu k was given between B and C. There's a rough surface and mu k is 0.2. So the angle is 30 minus the mass is 79.8. The sine of which angle? Now, the sine of which angle? The very same angle of 30. And this is equals to 70A. I hope that we are fine. Wonderful people. Let me just insert the laptop on a charger so that we may smoothly and comfortably continue with the lectures of Papa Fanzo. Right. Be that as it may, we just require a calculator to complete this and this. So I can go to my calculator very quickly on this app. I have 0.2. Multiply this 0.2 by 70. Multiply that with 9.8. And multiply all that by the cosine of 30. And find an answer of 118.8186854. Okay, so this is this. Let's go to this, and I can say 70 times 9.8 times the sine of 30, and I can find a value of 343 equals to 78. Like terms, we can add or subtract the values so that the force of tension minus, so I can just say answer, and I can say plus 118.818 6854, and this will be minus 461.818 6854 78. And I can leave this as my equation 1 since I have two unknowns. I don't have the tension, I don't have the acceleration, so I can leave this as equation 1 for the 70 kilogram block. And I can now go to the 12 kilogram block, and I know that I have the normal force counterbalanced by the component of weight, which is Fg perpendicular. Remember, we used this free body diagram, and this one is when we assumed that the object is moving from left, from the object is moving to the left. You remember we used this free body diagram. If the object is moving to the left, therefore tension is this, and friction and weight is that. So we used this. I think so. Yes, that's exactly what we did. So if we assume that the same for this, so if this is going to that, this is going down. So meaning if it is going down, the component of the weight, we will say it's positive, and the tension, we will say it is negative. So if we look at this, and this is going down, if it is going down, so I'm going to take mg, okay, let me say F net equals ma. Let me take out the page. I'm going to say that F net equals ma. So if we are going down, so meaning I have mg parallel, which subtracts the force of tension. Remember, this is a smooth, so there is no tension, so there are only two forces acting here, mg parallel and tension, and this is equals to the mass times the acceleration, which is 12a, and this is mg, the sine of theta, minus force of tension, 12a, 12 times 9.8, the sine, remember the angle there is 50, minus force of tension, 12a. And I can have 12 multiply this with 9.8 to the sine of 50. And I can have an answer of 90.086 82651 minus force of tension 12a. And as you can see here, I can okay, let me take this to the side because I want to make tension the subject of the formula. Minus force of tension 12a minus 90.086 82651. Okay, and dividing all this by -1, force of tension equals minus 12a plus 90.086 82651, and I can call this my equation 2, and I can substitute 2 in 1, and I can write my 1 force of tension minus 461.8186 854 equals 78. So in this equation where I see tension, I'm going to write this. I see tension, I'm writing minus 12a plus 90.086 82651 minus 461.8186 854, that is equals to 78. And then from there I can take this to that side and I can deal with these like terms. So I can say this minus 461.81 86, 854, and then I can have negative 371.73, 185.89 equals. So when you take this to the side, you will have 70A plus 12, which is 82A. Okay, you can divide by 82 by 82, and your acceleration will be this divided by 82, and we get negative 4.53 meters per second squared. And that becomes the acceleration. Now, we did not specify the direction because it is a vector. Now, remember, we said that this is the motion where this is moving to the left. So, negative will tell you that it is moving to the right. So, we will just say the acceleration, in other words, let's just say, let me think. Acceleration equals 4.53 meters per second squared to the right. That will be our acceleration, because the negative just tells us that this is moving to the right, because remember we said to the left, and then we find negative, we know that it is in the opposite direction, and this is your acceleration. Okay, that's fine. This is very much fine. We don't have a problem with that. And then from there, that was 2.2.2, we go to 2.3. And in 2.3 they say, if the angle of slope BC is decreased to 20, the slope of BC is being decreased to 20, will the friction force between the block and the slope increase, decrease, or remain the same? Friction force. Now, I can remember and then they say no calculations are needed. You will do these calculations aside. You will say, okay, I know that Fk equals UK times the normal, UK times mg, the cosine of theta. You will say 0.2 because this one doesn't change. They just said the angle. So you will say 70 times 9.8 times the cosine of 20. And you will compare the answer you get here with the answer you got here. This is the whole aim of what I'm trying to show you here. So you'll say 0.2 times 70 times 9.8, the cosine of a 20, and you will get 128.925 Newton. Now it was 118 and we are getting 128. So the first thing we will say, therefore, friction force will increase. That's the first thing. And why? Can you see that friction force is directly proportional to the normal force? This will increase because kinetic friction is directly proportional to the normal force. So meaning, if you increase the friction, the normal force will also increase, which is what? Which is mg perpendicular will also increase. So friction force will increase because kinetic friction is directly proportional to the normal force. Whether you show it like this or like that, I mix up these things a lot. but I think it's like this, something that is just worthy of noting. I don't know whether this is making sense to you, but it makes a lot of sense to myself. Right. So we are saying friction force will increase because kinetic friction is directly proportional to the normal force. I don't know how they will mark this, but this is the answer that we have. Very much the answer that I have. Right. And then that was at the end of question 2. I will see you in the next tutorial.